So on Monday, we learn about graph and we learn some basic things on graph. For example, the directed edge, undirected edge, and then directed graph, undirected graph. And we can see a lot of applications. So when you learn graph, it will be very useful. So we need to understand some basic terminology about graph. First is end vertices or endpoints. We call the endpoints or end vertices of an edge. If we have, okay, good. So if we have like this edge, okay, this is the edge A. So we will have the endpoints, which is U and V. So if we have the edge B, then the endpoints will be V and X. Edges incident on a vertex. We call it A, D, and V. They are incident on V. Okay. Because in V we have the edges A, D, and V. So other example, let's say we use U. What are the edges incident on U? We have A and C. Okay. Adjacent vertices. What are adjacent vertices? We call adjacent if there is a connection on edge. So we call U and V, they are adjacent. Why? Because we have one edge in between U and V. U and X, is it adjacent? No. Okay, because there is no direct edge. If we have direct edge, for example, W and Y, are they adjacent? Yes. Okay. We can also have another definition, degree of a vertex. X has 5 degree or degree of 5 because we have 1, 2, 3, 4, and 5. So what is the degree of vertex U? Here, 1 and 2. Okay. Parallel edges. H and I, they are parallel edges because one edge has its own name, H and I. And we can have another kind of edges, we call it self loop. So this is a self loop. So the edge is going to its own vertex. Okay. There is another terminology we call path. The path is a sequence of alternating vertices and edges. It begins with a vertex and it ends with a vertex. Each edge is preceded and followed by its endpoints. Okay. So do you still remember what is endpoints? Endpoints is any vertex that lies in the edge. Okay. So the every edge will be preceded and followed by its endpoint. We will have simple path. So simple path means path such that all its vertices and edges are distinct. Distinct. What is distinct? It means unique. Okay, no duplicate. So this is a simple path. P1. We want to start from V. Simple path. We want to start from P, and then we pass through P, which is the edge, and go to X, and then we go to the edge H, and then we go to Z. So we go, this is simple path because all are distinct. Okay. V, B, X, H, Z. So no duplication. But P2, okay, let's see, what is P2? We start from U, and then it goes to C, W, and then it goes to E, and then goes to X, and then goes to G, Y, F, O. Okay, we know that W is visited twice. Then this is a path, but it is not simple, because you will visit one place, or you will go pass through one edge more than one. So if you visit one vertex or one edge more than one, then it is not simple. We have cycle. Cycle means we have a circular sequence of alternating vertices and edges. Each edge is preceded and followed by its endpoint. So it's similar with path, but okay, but there is a difference. The difference will be okay, so like this one. Maybe I will explain first the simple cycle. The simple cycle is the same with the simple path. All vertex and edges are distinct. So it should be unique, no duplication. So for example, what is the cycle? A cycle is starting from one vertex and it will return to its own vertex. So we have V, and then it goes to B and X and G, and then Y, F, W, C, U, A, and then it returns back to V. We call this is cycle. And because all of them are unique or distinct, we call this is a simple cycle. What about C2? C2 start from U, and then it goes to C, W, E, X, G, and then Y, F, W. Okay, so W has 2 times. Then it is a cycle because it goes back again to U, but it visits W more than 1 time. And in the cycle, we do not put the vertex at the end again. So for example, we start from V. We don't put the V again at the end. But yeah, this is only symbol. Okay. Some people can write with the original vertex, which means we start from V and we return back to V. But yeah, this author use the symbol of this one to represent that it is a cycle. Okay, so that's also possible. So for example, if you usually you can do like this one. If you are a delivery person, okay? So you will deliver something and then you return back to your position. A simple path, yeah, it means if you visit from one vertex, if you visit half from your home, so it is your house and then you go to half, then it is a simple path. There are some properties. If you are using the graph, then yeah, you need to understand these properties. We have n, we have m, and we have degree of v. The property one mentioned that the degree of v, the summation of the degree of v equals to 2 multiplied by m. What is m? M is the number of edges. What is n? N is the number of vertices. Now let's see this example. We have 1, 2, 3, 4. So we have 4 vertices and we have m equals to 6. So we have 1, 2, 3, 4, 5, and 6. What about the degree of v? For every vertex, it has the same degree. Okay. 1, 2, 3, 1, 2, 3, and then 1, 2, 3, and then 1, 2, 3. Okay. So if we have this kind of graph, yeah, we can use this property. And the degree, the total degree, which is 3, yeah, for every vertex, we will do the summation. So it means 3 plus 3 plus 3 plus 3. So it is 12. Okay. And it equals to 2 multiplied by m. So 2 multiplied by m is 12. Then, yeah, it's the same. So the proof is each edge is counted twice. So every edge will be counted twice because we have one and another vertex. So if we have one vertex, if we have one edge, then we have 1 and 2. So that's why its edge is counted twice. What about the property 2? In an undirected graph, so we call this is undirected. Why? Undirected graph. Because there is no arrow. Okay? In the directed graph, we need to show the direction, or there should be an arrow. But in this case, there is no direction, there is no arrow. So we call it, this is undirected graph. In undirected graph, with no self loops, do you still remember? No self loops. Okay. There is no edge entering its own node and no multiple edges. No multiple edges means the same with the parallel edges. So if we have one node, we have one edges, there might be another edges. Okay. So for example, yeah, we can go to Seoul from Mohyun through Gundang or through Gwangju, then there can be multiple edges. So with this assumption, if there is no self loop and there is no multiple edges, we can use this property. Okay. M is less than equal to n multiplied by n minus 1 divided by 2. So let's see, 4 multiplied by n minus 1, this is 3, divided by 2. Then is 12 divided by 2. So is 6. Okay? So the number of edges will be less than or equal to 6 if it is an undirected graph with no self-loop and with no multiple edges. So the proof is, each vertex has degree at most n minus 1. So we have n equals to 4, then at most the degree is 3. So this is undirected graph. What about if we have directed graph? Okay, so it has different properties. Okay? And this is only for the undirected graph. Vertices and edges. Okay, we know that in a graph we will have vertices and edges. Vertices and edges. We model the abstraction as a combination of 3 data types: vertex, edge, and graph. So if you read any paper, non-moon, okay, so T is a graph, and there will be V and E, vertex and edge. A vertex is a lightweight object that stores an arbitrary element provided by the user. So in the first example, we learned about the airport code. So that's one possible vertex. In our real life, a vertex is a place. Okay? So you want to visit Omunguan, or you want to visit Hengyangguan, then it is a vertex. We assume it supports a method. So there will be an element to retrieve the stored element. So vertex is the concept in the graph, but we need to give the information. What is the meaning by the vertex? Is it a place? Is it a building? Is it a city name? Is it an airport? Or is it a supermarket, and etc.? So there should be one element to indicate what is the vertex. An edge stores an associated object. It can be a flight number, it can be a travel distance, it can be a cost, retrieved with the element method. So if I want to visit from Gonghakwan, and then I want to go to Dosokwan, so I can, for example, have like this arrow. Maybe the distance is 100 meters. So this is what we call as the associated object. Okay? It is travel distance, or it can be cost. So if I want to visit from Mohyun to Gwangju, there can be cost. If you take bus, it is bus fee. If you take taxi, then it is a taxi fee. If you take your car, maybe it is like the time distance from here to Gwangju. So that's what the meaning by object in the edge. In addition, we assume that an edge supports the following method: endpoints. So the endpoints means if I have an edge, there should be a vertex U and a vertex V. Okay, so vertex U and vertex V. So the vertex U is the origin of the edge, and the vertex V is the destination. So we have this one, U comma V. If it is a directed graph, then we can see something like this. For an undirected graph, the orientation is arbitrary. So I don't care about the direction. So this is the directed graph. If it is undirected, then you can have no arrow. Opposite. It means this is the other endpoint. So if I want to know the opposite of V, the opposite of V is U. If I have X and Z, the opposite of X is Z. Assuming vertex X is one endpoint of the edge, either origin or destination, and return the other endpoint. We can use this ADD. Okay. You can develop your own graph actually, but this is the basic one. You can improve more. For example, I want to know how many vertex, so we can get the vertex count. Vertices, so we will do the iteration for every vertices on the graph. Edge count, I want to know how many edges. Edges, so I will do the iteration for every of the edges. Get edge u comma v, so it returns the edge from vertex u and to vertex v if it exists. If it does not exist, then return none. For an undirected graph, there is no difference between get edge u comma v and get edge v comma u. Because there is no direction. If we use degree, v comma out equals to true. So I want to know the degree of v, and it is only out. Whenever you have the graph, if we have an undirected graph, it is okay. But if we have directed graph, then we call this is out, because the direction is out. But in this case, we call it this is in, because the edge in or enter the vertex. We can call this is outgoing, and this one we call it incoming. For an undirected graph, return the number of edges incident to vertex V. So it is only measuring how many edges, incident edges. For a directed graph, return the number of outgoing, because the out is true. If we change out equals to false, then if out equals to false, then it means I want to calculate the degree of V of incoming. So if out equals to true, then it is outgoing. If out equals to false, then it is incoming. Incident edges. I want to know the incident edges of V, and out equals to true. So it's also the same. If it is undirected, then you can have all the incident edges. Do the iteration of all edges incident to V. In the case of directed graph, the report outgoing edges by default. So this is by default, and it will report incoming edges if the parameter is set to false. We have insert vertex. So I want to insert any vertex which is, for example, X. If X is known, then we will create and return a new vertex which is X. And I can insert U comma V X. So it means I will create a new edge from vertex U to V and store the element X. For example, yeah, I want to go to Mohyun to Gwangju. I want to go from Mohyun to Gwangju, and I will take taxi. So there will be like cost. Remove vertex, remove edge. So it means just to delete if you don't need those vertex and edges. There are several kind of data structure for graph. First is edge list. What is the meaning by edge list? We will have the vertex object and we have the edge object. And we can have the vertex sequence and also the edge sequence. So in the vertex object, it means we have the element and the reference to position in the vertex sequence. This is the graph. And this is the object U, V, W, and Z. And I'm going to make it as an edge list. Edge list means we want to have this is the V. And in the V, we have the U, V, W, and Z. And then we need to define the edge object, which has the element, origin vertex object, destination vertex objects, and reference to position in edge sequence. So for example, I have an edge. This one I have E, F, G, H. This one E, and then F, and then G, and then H. So I can design this one. If it is an E, then it will connect to U and P. So E has the connection with U and P. What about G? So G is an object that is connected to U and W. F is an object to connect between U, V and W. V and W. And H is an object that is connected to W and Z. So this is a collection of vertex and it is a collection of edges. We call this is a sequence of vertex objects. This sequence 1, 2, 3, 4, and then we have also another sequence of an edge. 1, 2, 3, 4. Okay. So we call this is the edge list structure. We can have another kind of structure, we call it adjacency list structure. In the adjacency list structure, the incident sequence for each vertex. So sequence of reference to edge object of an incident edges. Incident edges. So this one, I know that it is if we have the information about V, then I will have E and F as the incident edges. If I have U, I will have E and G as the incident edges. Augmented edge objects, it means the reference to associated position to incident sequences of n vertices. So this, if you have like this is the vertex sequence. You have U, V, W, and Z. In U, we will have E and G. E and G. And then if there is another incident edges, for example, it goes here, so we can just add in this position. For example, V we have this F and E. We have E and F. And say if there is another edge like this one, then we will add at the end. That's the meaning by the augmented edge objects. Adjacency matrix structure. This is the most common approach. Maybe it is easier to understand because it is in the form of matrix. But there are several versions of the matrix, and this is the adjacency matrix structure. It is an edge list structure, and it has the augmented vertex objects, integer key or index associated with vertex. So for example, here I have U, V, W, and Z. So the U is index 0, V is index 1, 2 is for the W, and 3 is for Z. It is two-dimensional array adjacency array. So the reference to edge object for adjacent vertices, and it is null for non-adjacent vertices. For non-adjacent vertices. Okay, so okay. This is not. For example, this one. I want to know from U to U. Of course, this is null. I want to know from U to V. U to V, we have E. From V to U, so also we have E. From U to W, so we have G. So we just press what is the edge element in this matrix. So the performance of this ADT, if we just consider these three kind of data structure, suppose n is the number of vertices and m is the number of edges, and we assume there is no parallel edges and there is no self loops. So if we have the edge list and adjacency list, the space is the same, n plus m, n plus m. So it does not require a big space for using the edge list and adjacency list. We just have list. And what about finding the incident edges? Okay, it is OM. For the adjacent list, it is the O, big O, of degree of vertex. And if I want to check, are they adjacent or not? So if we use the edge list, it will take m times. But if it is adjacency list, it takes the minimum of the degree W or V, the degree of V. If it is the insertion, it takes only 1 because just insert. If we want to insert the edge, it's also 1 because it is just inserting. If we want to remove, we will check for every of the vertex. If we use the adjacency list, we will just have the degree of V. If we want to remove the edge, it is 1 and 1. Okay. So the two of them are quite similar in terms of the performance. And it seems that the performance of edge list and adjacency list is better than adjacency matrix. Why? You can see that the space, it requires n power of 2. Okay. If you have a matrix, of course, the matrix is like n and n. So n multiplied by n, it will be n power of 2. And when you are going to check the incident edges, it is only n times. if you are going to insert a vertex, so it will take at the worst case is n power of 2, the worst case. And if you want to remove the vertex, the worst case is n power of 2. But I think this one is easier for us to understand. And these two, yeah, you need to deal with many things if you want to develop your code. Yeah. I saw there are some teams who will do the graph on the team project. Yeah. So you can consider this one, whether you are using the adjacency matrix for the distance, or you are using the adjacency list or edge list. So there is a Python graph implementation, yeah, and there is a variant for using this Python graph using adjacency map. That's one reason why I explained to you about map last section. Yeah, we learned about map, and there is a way to implement graph using map or dictionary. For each vertex V, we use Python dictionary to represent a secondary incident map I, V. So the list V is replaced by a top level dictionary D that maps its vertex V to its incident map I, V. So note that we can iterate through all vertices by generating the set of keys for dictionary D. So if we know D is a dictionary, so we can have a set. Let's say I want to start from the index A. So A is the key. Okay. So the key A can be related to some other data structure. For example, if you are using the adjacency list, then it can be the name of the edge. For example, E, G, and you can make a list. So yeah, that kind of things, it can be one of the implementation. A vertex does not need to explicitly maintain a reference to its position D because it can be determined on one expected time. If we use the map, we just insert without sequencing or without ordering. We learn about the unsorted list, unsorted sequence, unsorted list. If you use the map, then the performance is O1. Running time bounds for the adjacency list graph ADT operation given above become expected bounds. Expected bounds means, yeah, it will be in the boundary. So this is the class. This is the Vertex class. You will see the constructor and what is the element or what is the name of the vertex. Has, yeah, it will be allowed for you to make a key from this vertex. And then we have edge. Okay. So there is an origin, destination, and what is the element. And then we know the endpoints, and then the opposite, and what is the element. And then again, we have the has to determine for the key or map. And if you are making a graph, so this is a vertex, and this is edge, and this is the graph. So you will define the class graph. We will have the constructor, and then you will define what is the outgoing and what is the incoming. And I want to check whether it is a directed graph or not. And I want to check how many vertex and what is the vertices. And I want to check how many edges and what are the edges. Get edge, degree, incident edges, insert vertex, insert edge. So those are the method that I explained before. Okay. I think we will take a look on the code. So in the graph, yeah, we have vertex. This is the code for the vertex. And this is the code for the edge. And this is the graph method. So we can construct directed equals to false. So it means if you want to make a directed graph, you can put it true. But if it is no definition, then the default will be, yeah, the directed equals to false. So it means undirected. Validate vertex, yeah, it means you want to see whether the graph has the vertex that you define or not. So all the vertex already in this object or not. Is directed, yeah, you know, we want to check whether it is a directed graph. And then vertex count, vertices, edge count, edges, get edge, degree. Yeah, those are what we already learned. Like this one, outgoing true. So this is the default. If it is false, then yeah, we can change to the undirected graph. This is also outgoing true. We can change to false if it is undirected graph. Okay. I will explain more after the break now.